Hi everyone. Today we're going to be talking about the Good and Annan chapter 11.4, which is about series solutions at what are called regular singular points for a differential equation. So this is going to be an extension of series methods to places where we can't assume that the series has a power series solution, but we can modify it so that even though it's not actually a power series, we can use the same techniques where we can use recursion to figure out a pattern of coefficients. Because we're going to be looking at places where there are asymptotes in a function, there are going to be some restrictions on exactly how bad the asymptotes can be, and we can still handle that with the methods we're going to introduce here. So to start with, I want you to think about the differential equation that we've been writing down. Y prime prime plus p of x y prime plus q of x y is equal to 0. This differential equation we knew had a series solution when p of x and q of x were analytic. So the question that we have to ask is, what if they aren't? That is, can we find a solution anyway, even if p and q have an asymptote at some point? To say that function is not analytic, we're going to think of as having an asymptote. So a 0 in the denominator is how we have analyticity fail. First, we're going to need some terminology. Points where a differential equation fails to have its coefficient functions analytic are going to be called singular points. X is equal to x naught is called a singular point for a differential equation if p and q fail to be analytic there. So again, you can think of having asymptotes as being how a function can fail to be analytic. Singular points come in two varieties. There's nice singularities and there's not nice singularities. We're going to start by classifying the singularities that we can handle. So those are the ones that are nice enough that we can still use the series ideas that we've developed to attack them. And then every other singularity we're going to throw up into a different category that's going to be the bad singularities. So now, given the same sort of differential equation, so we're going to assume a singular differential equation, we're going to define new equations, p hat and q hat. And the way that we're going to define them is we're going to look where the singularity is, and we're going to see if we can cancel that out of the denominator. So essentially that's what the x naught and the x minus x naught squared here are doing, right? Is they're canceling any possible copies of x minus x naught in the denominator of the function. If it's the case that we can multiply through p by x minus x naught and q by x minus x naught squared, and we get analytic functions, then we're going to call that sort of point a regular singular point. So the fact that we've had this square term here means that this is going to work because it's a second order equation. There are regular singular points for higher order equations as well, but then you have more coefficient functions, and you need it to be the case that in each one that you can cancel out a higher and higher power of x minus x naught in the denominator. So basically what we've done here is we've set up a regime where if we have a certain kind of singularity, then we're going to be able to use series methods on it. And those points are called regular singular points. And we'll talk about how to calculate this condition with some examples when I'm done with the definition. Otherwise, x naught is an irregular singular point. So irregular singular points are much more difficult to deal with. And there are methods for doing so, but that's going to be beyond the scope of the course. I'll give you some resources if you're interested in how this works. So your first response to talking about singular points in a differential equation might be to wonder why it matters. Why do we need to know how a differential equation acts when we get close to places where the functions that define the differential equation have asymptotes? If you want to put this in the context of physical problems, you can think of setting up a system for describing how a physical system works, and developing a solution everywhere that the system is nice is great, but the physical system itself could evolve in such a way that the inputs approach a singular value. If you've designed that system, you need to know what happens to the system, whether it's physical, software, chemical, what have you. You need to know what happens as the inputs get closer and closer to that singular point for the defining functions. What do the solutions do? It could be the case the solutions stay well behaved and you have a system that holds together. It could be the case that as you approach a singular point, the system blows up in some way. Either way, that's important information to know. And that's why we're interested in looking at the boundaries of where our systems are defined, which is where singularities occur. So now let's do an example of classifying singularities. When you're identifying singularities, it's important to first be able to identify where they are. So the functions p and q here are given by these rational functions. They obviously have singularities at x equals 0 and x equals 1. So let's see if we can classify what those singularities are. x equals 0 definitely puts a 0 in the denominator of p, and it definitely puts a 0 in the denominator of q. But is it a regular singularity or an irregular one? Well, we can check by looking at the functions p hat and q hat. Remember that p hat is equal to x minus 0 times p, which in this case is equal to x times 1 over x minus 1 squared times x, which is 1 over x minus 1 squared. And that function, even though it still has that asymptote at 1, it's analytic at 0, because this function is perfectly happy at x equals 0. There's no asymptote. This function is analytic at x is equal to 0. We can check q using its version of that condition, which is instead of multiplying by x minus 0, we multiply by x minus 0 squared. Q hat is x minus 0 squared q, which is equal to x over x minus 1 to the third. This function is also analytic at 0. Because just like p hat, it doesn't have an asymptote at x equals 0 once I have canceled it out by multiplying by x squared. In some sense, what we're doing is we're measuring the worst possible singular behavior that p and q can have. The conclusion is because p hat is analytic and q hat is analytic, then x is equal to 0 is a regular singular point. What about x is equal to 1? Well, it's pretty obvious that if you multiply even p through by x minus 1, you're still going to have an x minus 1 in the denominator. So if you have x is equal to 1, then your p hat function is equal to x minus 1 times 1 over x times x minus 1 squared. In that case, what you're going to end up with is 1 over x times x minus 1, which is still not analytic at x is equal to 1. So this is not analytic at 1, and that means that 1 is an irregular singular point because the pole, or the 0 in the denominator for p hat, is just too big. It can't be canceled out. So we say it's an irregular singular point. Functions that have regular singular points have a very nice form that we can always write them in once we have one. So the general form of an equation with a regular singular point at 0 is given by x squared y prime prime plus x p of x y prime plus q of x y is equal to 0, where p and q are analytic at 0. So no matter what I started with, if it meets the definition of a regular singular point, I can transform it into an equation that looks like this. And remember to say that p and q are analytic at 0 means that they have series there. So this is the equation that I want to work with if I know that I've got a regular singular point. No matter what I start with, I can always do the theory in terms of this. In a previous class, you may have learned a special form of this equation that you have solutions for, called the Cauchy-Euler equations. And Cauchy-Euler equations are of this form. In this particular form of the equation, p naught and q naught are just constants. And of course, those are analytic functions because they're very short power series if they only consist of their constant terms. So Cauchy-Euler equations came up in the earlier class with a method of solution where one of the very few equations that were non-constant that we had any approach to solving at all. So the general method of solution that you learned for dealing with Cauchy-Euler equations was in terms of something called the indicial equation. And it's an auxiliary equation related to the Cauchy-Euler equation that tells you what form the solutions must take. And that's actually going to be the basis that we're going to use for solving this equation. We're going to start by looking at solutions to the Cauchy-Euler equation, and then we're going to try to use the method that we did there to reconstruct what happens if we have multiple terms here and not just constants. So here's the theorem about Cauchy-Euler equations. And we're not going to go through the derivation. I'm just going to tell you what the solutions are. If you're interested in looking through how this was derived, you can go back to that chapter in Good and Annan, and I'll link to that in the lesson page when I post this. What the theorem says is that if you have an equation that looks like x squared y double prime plus x p naught y prime plus q naught y, then you have solutions on the positive real line of the form x to the r, where the r in the x to the r comes from the indicial equation, which is in terms of p naught and q naught. So it's this quadratic equation down here where you have r times r minus 1, and then you've got a term that contains the p naught and a constant term. But the same approach here, where we try to reduce the equation into the roots of some sort of characteristic or indicial equation, constructing the solution, that's going to be the core of how we approach the general solution to the equations that we're working on. I don't want to give you a proof of how the general theorem for regular singular points works, but I would like to give you some idea of what the intuition is. So let's just assume that instead of a Cauchy-Euler equation, that we have the equation for a general regular singular point. So that is, let's assume that we have, because p of x and q of x are analytic, if we're at a regular singular point at 0, then that means that p and q have power series, which means I could write out p of x in terms of its power series, and I could write q of x the same way. So now what happens if we take those power series, which are abstract at this point, and we plug them back up into the equation here for the regular singular point at 0? What we get is the following. So this doesn't look like we've made any progress, right? We've plugged in the power series, now we've got this nasty equation. If I put a very small value of x into this equation right here, it's still part of the solution set because we're still working on 0 to infinity. So if you put a little tiny small x in here, what ends up happening is all of the terms with the x's in them get really, really small. Right? After all, if x is 0.1 and you take it to the 13th power, you get something tiny. 0.0000000000001 or something like that. What I'm going to do is I'm going to try to guess the solution really close to x equals 0, and then that will be the form of the solution that I'm going to go hunting for. So what we're going to do is, if we let x be very close to 0, then this equation sort of looks like a Cauchy-Euler equation. This stuff all kind of goes to 0, and this whole equation ends up looking like x squared y prime prime plus x p naught y prime plus q naught y is equal to 0. So this is about equal to that. They're not the same, but it looks like this. And we already know that the solution in this case has solutions that look like x to the r, where r comes from the initial equation. In this case, we would have solutions that look like y is equal to x to the r, where r is a root to this equation. So this tells us what happens when x is very close to the origin, when x is very small. I can find solutions of the form x to the r subject to r being a solution to r times r minus 1 plus p naught r plus q naught is equal to 0. That takes care of what is going on up here when x is very close to 0. Well, what about the rest of the behavior of the solution far away from 0? Well, we assume that there's a power series that describes the rest of it. And this is why the power series method doesn't work by itself, is because r doesn't have to be an integer. R could be a fraction, in which case you're not looking at a power series. So what we do is we say the x to the r takes care of the way this equation works near 0, and then there's going to be a power series attached to it that takes over when x is far away from 0. So the general guess for the solutions to this equation are going to be that at y is equal to x to the r times some power series, where this kind of takes care of x's that are close to 0, and this takes care of what happens on the rest of the interval from 0 to infinity. And this turns out to be the correct thing to guess. This type of series is not called a Taylor series or a power series, it's called a Frobenius series. So this object right here, where I take a power series and I multiply it by some x to the r, where r isn't necessarily an integer, is called a Frobenius series. And it generalizes power series. Every power series is a Frobenius series, but not every Frobenius series is a power series. In particular, the r could be negative even, so you could have negative powers inside of this series once you multiply the r inside. But this is the correct object for finding series solutions when we have a regular singular point. And we'll write that down in a theorem in the easiest case next. So let's walk through what this theorem says. So this is a brick of text here. But the basic ideas are we're just encapsulating what we've said over the previous slides. So we're going to assume that we're on the positive numbers so that the Cauchy-Euler condition holds. That's to get us Cauchy-Euler. Now we're going to suppose that we have a second order differential equation of the right form that will give us a regular singular point. Then we're going to assume that p and q are analytic because we know that we need a regular singular point. So p and q are analytic with a positive radius of convergence, r greater than 0. We're going to need to write p and q as power series because we need the p naught and the q naught. We can think about that as that's the same as p of 0 and q of 0. But the point is I need those constants because I'm going to use them in this equation. Okay, so I write p and q as series, and I'm going to let r1 and r2 be roots of the initial equation, which is right here. And I'm going to let r1 be greater than r2 if they're different from each other. we're going to be considering the case where R1 and R2 are distinct. So if R1 and R2 are distinct, let's let R1 be the bigger one. Then, if all of that holds, then I know that I've got at least one Frobenius series solution to this equation of this form. y1 of x is x to the r1 times some power series, which I'm going to figure out by using a recursion relation. Now, where does the second linearly independent solution come from? And the answer depends on how r1 and r2 are set up. If r1 and r2 are distinct, that is, they're not the same number, and r1 minus r2 is not an integer, that is, they're not exactly 1 or 2 or 3 units apart, then I actually have a second Frobenius series solution as well. To encapsulate what I just said, the second half of the theorem says that if r1 and r2 are distinct real numbers and they don't differ by an integer, then we have a second Frobenius series solution that will differ from the first one, where now we've got x to the r2 here. Part of the reason why, if they're distinct, we don't get two different Frobenius series is that we don't get series that are linearly independent. If x to the r1 and x to the r2 are the same thing, then it turns out to be the case that they're constant multiples of each other. Okay, so this is a lot, but what it really boils down to in the end, when you take all the technical language out, is we're going to compute p naught, which is just p of 0, and we're going to compute q naught, which is q of 0. If you think about what the power series is doing, if you write out the power series and put in 0, then all the terms disappear except for the constant term. So we compute p of 0 and q of 0. Then we solve this equation for the roots r1 and r2. Because we're in the chapter where I've introduced Frobenius theory, then you know that r1 and r2 are going to be distinct and they're not going to differ by an integer, because that involves all the complications that come later. Once I've done that, now I'm going to go looking for a Frobenius solution. So 3, I assume that I have a solution of the form y is equal to x to the r1 sum from n equals 0 to infinity of an x to the n. And I should say here, I'm assuming I'm taking the larger of the two roots. So take the r1 to be whatever the bigger of the two roots is. Once you've made this assumption, you use recursion, and you do the recursion exactly the way we did it in the last section. Use recursion to find a pattern for the ans. And then step 5 is you just go to 3, but with r2. So you do it again where you have another solution in terms of r2. So as you can imagine, there's quite a bit of computation to be done in a problem like this, but they're not as bad as they look. They're essentially identical to the problems that we did in the last section. So let me write one of those down as an example, and we can see exactly how this works.